The second step for finding the Thevenin equivalent circuit is to calculate that RTH, that's that parameter. Once again, we are going to make a rule. We don't have to memorize that rule, we can find it out from this circuit. So if we make this A and B terminals short circuit, there's going to be a current passing through. This is called short circuit current. So that means that VTH is the same voltage of this resistance voltage. So if I use the resistance definition relation, then RTH is VTH over ISC. So that is the rule. If you somehow calculate this short circuit current in the circuit given to you, if we already find that VTH, so divide the VTH to ISC that just we found, that is equal to RTH. That is the rule. So I'm going to apply that rule to the circuit given to us, to this one. So that means we're going to make this A and B terminals short circuit and calculate that ISC. How we are going to do that? So there are this short circuit affects some other elements, voltages and currents. How it affects? When you make short circuit here, that means you made VAB equal to 0. Isn't it? Short circuit means that. That is short circuit current. So this voltage is 0, that means this resistance voltage is 0. If, by definition, if the resistance voltage is 0, then since the R is different from 0, resistance current is 0, we already explained that this element is going to disappear. We are going to remove it from the circuit. At the same time, since this VAB voltage is 0, this voltage also controls this dependent voltage source voltage. So that's going to be 0. That V is the same as VAB. We made the VAB to 0. That means we made this dependent voltage source voltage short circuit. So our new circuit becomes this 8 volt independent voltage source, a resistance of which is 10K, and this is short circuit, we just explained. Short circuit, the voltage of this dependent voltage source, because of that V, that is VAB is equal to 0. Then we've got this dependent current source, of which current depends on this current here, isn't it? That I here. So we said we are going to remove that resistor, since voltage and current both of them 0, so we remove that and then calculate that ISC. So that is, we transferred the problem to this problem. In this circuit, we are going to calculate that ISC. So if you write Kirchhoff current law equations for this node, that's going to be both of them out of the node, ISC plus 10I is equal to 0. This is Kirchhoff current law equation for this node, isn't it? So ISC is equal minus 10I. So we need to calculate that I here. This is not the ISC that I would like to find here. When I said ISC, you've got to calculate the ISC in terms of independent sources. So that means that's not the end of it. So we are going to transfer this I to the independent voltage source voltage. How I am going to transfer it? So if you look at this left hand side here, this 8 volt is the same as this 10K resistance voltage. So if I use the definition relation, that I is 8 over 10K. That is this resistance definition relation. So if I put this here, it becomes minus 10, 8 over 10k. So 10 has gone. So if you do the calculation, it's going to be ISC minus 8 milliamp. Now this is the thing that I am talking about, not this. I mean, you don't call this as you calculated the ISC. You say you calculate the ISC, that is the value you end up with. So we're going to put this here, then RTH, we already found VTH 3 volts, over minus 8 milliamp, you end up with minus 375. So it's a negative resistance. You might say that this resistance, this cannot be true, but we still accept that, because in here we are using this resistance value as a mathematical tool, you see. For the calculation, I can take this. I'm not going to buy a resistance like that in the market. That's why I will be using this in the mathematics. So it is reasonable, that conclusion. If it were positive, then we could say that we don't need to use 4 elements in here. You can replace all of them with that just one resistor value. That's the end of this.